Everybody, this is Jim Neeb again. Just a couple days ago, I did a video on calibrating the backlash in your AVID CNC machine with the new EX controller, which is a Centroid CNC12 software comboed with the Acorn board. So I've done a video on this back on the Mach 4 days. So a couple people have asked for linearity and backlash calibration videos to go with the Centroid hardware. So I did the backlash in a separate video. This is going to be for linearity. So does it move the amount of distance that you programmed it properly? So we're going to do X, Y, and Z and show how to set that in the CNC software, how to calculate based on the error, how to calculate what it should be. And then you'll see my results here. In the end, I was pretty happy. The machine was probably in X, it was probably off by 50 thousandths in the 4 feet, and I got it down to probably 10 or less. And then the data is interesting. You can see how much localized error there is. Like if you go 1 inch, 2 inch, 3 inch, 4 inch and measure the error, you can kind of see there's, even if you get the linearity calibrated out over the long distance, there's still a localized error step to step of probably plus or minus 5 thousandths. And that's why you'll see people with a lot of experience with mills and stuff always tell you, don't expect too much from a CNC router because these things are a lot bigger and sloppier and don't have the tolerances of a good mill. But on the other hand, if you play around with them a little bit, you can dial them in pretty good. And, like plus or minus 5 thousandths over 4 feet with this much weight and a extruded aluminum frame is pretty good, I think. So especially for woodworking, because 5 thousandths is nothing compared to wood expansion. So anyway, check out the video. If you have any questions, let me know. So here's the setup I'm using to measure my linearity. I use a long caliper. I have an 8-inch. This is my better quality one. I also have this 12-inch one that's it's a little lower quality one, but the reason I have two of them on here is I compared them over the first 6 or 7 inches of travel, because this is only an 8-inch one, and I got results within 5/10 thousandths of an inch. So I think they're reasonably accurate, for sure within 1 thousandth of an inch. But this is the setup. I clamped down the head of the caliper to a block, and I put a dowel in my chuck here, and I use that to just push this along. So I go over to the front of this, set my caliper, zero it out at that point, and then I incrementally, I just use the MDI window, and I set it to G1, X1, G1, X2, G1, X3, G1, X4, all the way up to 10, because that's about the full length that I can do on this 12-inch caliper because I lose a little bit up here for the clamping part. So I go 10 measurements from 0 to 10, and then I walk my way back down, and then I walk my way back up. And that takes into account any backlash in the two directions, as well as gives me some idea of what kind of variability I'm getting. So that way, if there's a little, and I can also see the non-linearity from the two endpoints too, because if I were just to take say a 0 and a 10-inch reading, I may have a whole lot of non-linearity in between that I don't know about. So I was really curious to see what this would look like. So the other thing you want to do is make sure that your caliper is running parallel to the axis you're running. So what I do there is I'll just come in back here first when I'm clamping this down, and I'll jog my pin right up next to the caliper body, and then I'll jog down to this side, and I'll make sure I have basically it touching all the way, and then I know this is, in this case, I'm measuring my X travel, and I'm setting the caliper up with the same Y position at both ends. In other words, it's parallel with the X axis. So you need to do that. Otherwise, you're kind of, you're setting a triangle up, and you'll get some some error with your measurements. So I did all of that a couple of times, and then I plotted it. So this reflection right here. So this is my table. What I did was, here's the actual, or the program value. So these are my MDI commands, from 0 to 10 inches. And then this pass is going from 0 on the left to 10 inches on the right. These are the actual measurements off the caliper. Then I just simply move to the left direction. So I'm using my MDI commands, 10, 9, 8, 7, all the way down. And then I come and do it again. And that way, like I said, the difference between the first and the second column and the second and the third may have some shift due to backlash, and I want to see that too. And then what I do here is I just simply subtract the actual measurement from the ideal program value, and I get the error, and then I plotted it here. So you can see that, again, this is the original AVID CNC provided revolutions per inch. So you can see there's some nonlinearity there. At 0, 0, 4, and 10, the values are a little bit lower, and then they have this little kind of double hump there. That's to be expected. No system is perfectly linear. You can also see even though in the last video I did, I showed correcting for backlash, you can still see there's a little bit of residual backlash in here, because the orange one is the second. That's the left going measurements, and then the other two under the orange are the right going measurements. So there's a little bit of backlash effect in there yet. At some points it's a couple thousandths. At some points, like in the middle here, it's none. But the most important thing that I'm looking for here is there's a general trend that, at 10 inches I'm down here, but if I try to kind of take the average of that line, I'm about 13 thousandths off at 10 inches, or it's about a thousandth of an inch error per inch of programmed movement, which isn't horrible. It's for a CNC router, that's fine. In 4 feet, that means I'll be off by 40 thousandths of an inch. But my purpose here is to demonstrate how to do this, and to measure how your system is performing. I would guess that the value that comes with the AVID machine and All Axis is probably fine for most people. I just like to play around and tweak things. And then, if you're setting up your own machine and you're not buying an AVID, if you're just buying a Centroid CNC12 and an Acorn or something, and building your own system, you need to know how to do this, because it won't come programmed at all. So that's the purpose for doing this. So down below here is the correction. So what I did was I calculated a new revolutions per inch value and plugged it in, and this is the result. So now you can still see I sort of have a general hump like I did up here, and it looks like it's bigger here, but look at the error is much, much smaller. So, up here we're getting up to 12, 14 thousandths. Down here, the peak is more like 4 thousandths. So you can see I flattened out the trend. So I essentially, in the 10 inches, come back to where I am. And, in the middle here, I'm off by 4 thousandths. So, ultimately, to see the error across my whole 4 feet, I would have to measure this in a similar fashion across 4 feet. Well, I don't have a 4-foot caliper, and I'm not going to buy one for this. But again, this demonstrates how you do this, and that the CNC12 software does level this out pretty easily. So, now I'm probably across this 10 inches, I'm plus or minus 4 thousandths in accuracy. Some of that's due to localized nonlinearity. But I did get the slope out of this, for the most part. So I know that in 4 feet, I won't have 40 thousandths anymore. Whether this value comes back up, I don't know. That could be attributed to, like, one of the pulleys isn't perfectly concentric or something like that. Who knows? It might be, In the case of the motor, I doubt if it's the motor, because this is actually about 10 revolutions of the motor. So I should see, because the way the gears and the pulleys are, it's about an inch per revolution. If there was something in the motor itself, I should see that repeat like 10 times across this, and I don't really. So it's not, I don't think it's some kind of nonlinear in the motor. It's something else. And again, I don't think it's my caliper, because I've compared two calipers against each other and I got exactly the same results. So this is as good as my system is at this point. Now, I should point out that the CNC12 software is extremely capable. It actually has a compensation capability where you could go in each axis and program a different offset value at each distance, like at 1 inch, at 2 inches, at 3 inches. You could build that whole table and plug it in and compensate this all the way. That's a really advanced thing to do. Certainly, this accuracy that you're seeing here is more than adequate for something that you're going to, a multi-foot wide CNC router table. So it's not worth doing, but I just wanted to say that CNC12 has that capability. And in addition to that, they've recently added, I think it's still a beta feature, but they've added something, what they call volumetric compensation, where say your rail, say your gantry has a bow in it, so that the Y distance changes as X changes, right? So like if you had a big old U-shaped gantry, you would have a different position in Y as your X moved up and down that crooked gantry. They actually have a method to compensate for that, where you could have different Y measurements for different positions in X, and the same thing on Y. For example, if your table rails are bowed, you can compensate X for Y and Y for X. So that's, again, another very advanced thing. I'm not going to cover it here. I think for CNC routers, just basic linearity is about as far as you'd ever want to go. And again, I want to stress that for most people, you don't need to touch the values at all, at least on the AVID machines as they come, unless you just like playing around with your machine, or you want to get the very best in overall accuracy. All right, let's take a look at where you actually set this. So if you watch my video that I did a couple days ago on backlash compensation, it's in the same place. So if we go to the utility menu, and then to advanced configuration, and then to machine, and to motor, you see we're in the same area where we made the lash compensation adjustments the other day. So over here is the motor revolutions per inch. So again, as I mentioned the other day, you don't mess with these numbers here, the motor steps per revolution. So that's meant to just represent the motor's resolution per revolution. So that could be 1,000, that could be well, it can't be lower than 1,600, I believe is the minimum. But this basically should be set up based on your motor's resolution, or whatever micro stepping you've programmed in your stepper driver, if you have a stepper motor. In the case of me, I have servos, and this is the resolution of the motor. So over here then is the number of revolutions per inch. So in this case, you can see I'm very close to 1. So that means 1 revolution is about an inch, and that means that there's 2,000 steps. That means 1 step is about half of a thousandth, or 5/10,000ths of an inch. That's kind of my, that's the resolution of my system. Now the encoders have much more resolution than that. So inside those servo motors, they can compensate to get really close to that 1/2,000ths. But from the CNC12 software side, it can't compensate any of these numbers any better than 1 step, obviously. And so that's the basic resolution. So this, these last few digits here, this is where that basic linearity adjustment is made. And so let's go to the grease board and I'll explain how you can accurately calculate this. First, I want to say you could probably guess at this because, as I said, we're about one revolution per inch. So you could almost say, well, if I'm off by a thousandth, then I'll just change this 9 here to well, it would round up. This 99 would round up to 2. So you could kind of guess at what this number is, but I'm going to go show you on the grace board how to calculate this. And this came out just about perfect the first time I did it. So I know this works really well. Okay, here's how we calculate the value based on our measurements and what the initial setting is. So if we just look at the ratio of the current revolutions per inch setting that's in CNC12, it's the factory value from AVID, divided by the measured distance, which is the actual distance. So these are kind of the two actual values we have right now. This is what's in the software for the revolutions per inch. This is what we're actually measuring over that distance. And then that should equal what we need to change it to over the ideal distance. So the ideal distance is our 10 inches that we're using with the caliper. It could be 1 inch or you know whatever value you want to use. That ideal value corresponds to what you actually measured for it, and this desired new software setting corresponds to the existing software setting. So if we solve for the new setting, we get the current revolution per inch setting times the ratio of the ideal distance over the actual current distance. So in this case, we take this is the software setting. I'm coming up short here in my measurements versus the 10 inch that it's supposed to be. So we get a value that's just a little bit bigger than the original value here. And we had 13 thousandths, as I mentioned. The ratio is just about 1 for the turns per inch. So because I was off 13 thousandths, you'd expect that I would have about a 13 thousandths adjustment in this number, which you see is this is 185 to 199. So you could, like I said, you could almost guess just from looking at the numbers in your error without actually doing the calculations what the new value should be. But this is, if you want to actually calculate the exact number, this is how you would do it. All right, we just looked at the results from calibrating the x-axis up here where we had this slope and we basically turned the slope down so it didn't have a slope anymore. Then I went back and did the y, and the raw error here is not nearly as bad. You can see plus or minus 3 thousandths about of error. The slope is a little bit hard to tell. You could almost argue that it's already flat. You know, just kind of depends. Like if you took out the 0 point, then it would look like it has a pretty sharp uptick here. So this is a case where I'm going to leave it alone because it's not very big. Over 10 inches, it almost recovers back to 0. But I want to double check this with the ruler over the total travel on my machine, just to make sure that I'm not misinterpreting this. You know, again, all it takes is a couple of missed points or trying to read this at the wrong place to maybe throw it off for the 4 foot of the table. So I'm going to leave the Y with the factory settings for now. Then when we go look at the Z error, you can see this is a ball screw Z axis. It's not rack and pinion drive with a belt like the other one. So it behaves a little different. You know, if you notice here, you got a lot of localized inch to inch variation on X and Y, whereas Z is a lot tighter, but it definitely has some slope error, but it's pretty small. I mean, if you look at the scale here, we're only talking about 1.5 thousandths up to the 7 inches, and then there's a little bit of an outlier up here. So what I did was I took I took this data and drew a line through here, and I said in 8 inches, I've got about 1.5 thousandths of error. So I recalculated, just like I showed you for the z-axis, recalculated the number, and the number of turns, go to the table here, is 2.54 in the straight up factory settings from AVID. So I set it to 2.5405 originally as a first try to correct this, and it didn't quite correct it. It still had a little slope. So then I turned it back to 2.541, and then that's what I got, this result error here. And so it's basically no error for the first couple inches of travel, then it comes down and back up, but it's no slope again here across the 8 inches of travel that I can measure on this axis. This is a 14-inch z-axis, 14 inches of travel, but I don't have a caliper that long, but I am measuring it in the bottom 8 inches of travel, which is all I really care about. I don't cut or anything above that anyhow. So this is the area that counts, and that's the nice thing about the z-axis. It's not huge on this machine, so I can actually measure it off the full travel. So this is really good. Like minus 1,000th and plus half a thousandth is my worst case peak to peak error across this 8 inches after calibration. So it's pretty easy to really dial this in finely if you want, or in a really fine manner. So it's very good. Now, as I said, for the Y error, I'm a little concerned about this, so that needs a double check. So what I'm going to do there in the end is lay my tape measure. It's the only thing I have that's 4 feet long to measure with across the whole thing. I'm going to take a fine sharp tip V-bit and basically measure, some amount of the total travel, probably about 45 inches is what I'll be able to do, and make sure that I didn't do something gross here and like misinterpret it. Like I said, it's hard to tell here. If I go from 0 to 10, then I think this is really good. But what if like 1 to 8 was a more representative value, right? Then that slope would cause a more error that I'd want to calibrate out. So that's how you double check it, is do it over the full length of the bed, just as a backup. And in fact, you don't have to have a caliper if you just want to do X and Y across the bed with the tape measure. That is not a bad way to do it. A regular tape measure or maybe a precision ruler that's long with laser marked gradicules would be even better. But even a tape measure, because it's such a long distance, the error is divided out per inch to be pretty small as far as your ability to read on those lines. So multiple ways to use for measurement on this calibration method. Okay, I did go back and use the tape measure to double check my X and Y, just because I was measuring over a 10-inch range with the caliper, and my table is 4 foot by 4 foot, and especially on Y because I was concerned about that the shape of that curve in the end. I flattened it out much better than it was originally, but there was still some concern whether I was should be picking the end points or some other point there. So this was a double check. It turned out it worked out great. I couldn't really, I had exactly what the tape said versus the DRO, as well as I could read with with the tip of a sharp bit on the tape measure itself, which is just my ability to read. That's probably plus or minus 10,000. So I think I picked a pretty good slope when I did the calibration there. All right, and that's it. I think this, combined with the previous video I did on backlash, covers the how to do it on new Centroid software and hardware. Well, it's really just a software thing in this case. I didn't cover the more advanced features that I really don't think you need on a CNC router, but this covers the basic linearity. And if you have any questions, please leave a comment down below. Thank you.